Have you ever wondered why our planet has had massive ice ages? We're talking about times when enormous sheets of ice, kilometers thick, covered huge parts of North America and Europe. It sounds like something from a movie, but it's a real part of Earth's history. These colossal changes didn't happen overnight. They followed a slow, steady rhythm, a kind of planetary dance that takes place over hundreds of thousands of years. It's a natural cycle of warming and cooling that has shaped our world in profound ways, long before humans were driving cars or building factories. This grand climate story is written in the very way our planet moves through space. The secret to understanding these long-term climate shifts lies in the sky. A brilliant scientist named Milankovitch figured this out about 100 years ago. He realized that Earth's relationship with the sun isn't perfectly constant. Our planet has a few wobbles and wiggles in its orbit, and rotation. He proposed that these small, predictable changes in Earth's movements could alter the amount of sunlight reaching different parts of our planet at different times of the year. These variations, now called Milankovitch cycles, are the master choreographers of Earth's long-term climate dance, setting the stage for the coming and going of immense ice ages. Think of it like adjusting a giant thermostat for the entire planet, but the dial turns incredibly slowly. These cycles don't change the total amount of sunlight the Earth gets over a whole year by very much. Instead, they change where and when that sunlight arrives. It's all about distribution. Is the sunlight more concentrated at the poles in the summer? Or is it more spread out? These seemingly minor adjustments in solar energy, particularly during the northern hemisphere summer, are powerful enough to either plunge our world into a deep freeze or pull it out into a warmer period like the one we're in today. So, let's get into it. We're going on an astronomical journey to uncover these amazing planetary movements. We'll explore Earth's tilt, the changing shape of its orbit, and its slow, top-like wobble. By the end, you'll see how these three celestial rhythms work together, like instruments in an orchestra, to create the grand symphony of Earth's ice ages. Understanding this natural beat helps us appreciate the deep, powerful forces that have governed our climate for eons, and provides a crucial baseline for understanding the changes our planet is experiencing today. Science is the key to unlocking these incredible secrets. Now you might be thinking, why all the focus on the northern hemisphere? Doesn't the southern hemisphere get sunlight too? That's a great question. The answer has to do with a simple difference between the two halves of our planet, land versus water. Take a look at a globe. You'll notice that the northern hemisphere contains most of the Earth's land masses, North America, Europe, and Asia. The southern hemisphere, by contrast, is mostly covered by vast oceans. This geographical setup is incredibly important for starting or ending an ice age, making the north the main stage for this climate drama. Land and water behave very differently when it comes to temperature. Land heats up and cools down much more quickly than water. Think about a hot summer day at the beach. The sand can get scorching hot under your feet while the ocean water stays refreshingly cool. That's because water has a high heat capacity. It can absorb a lot of energy without changing its temperature much. This difference means it's much easier for vast sheets of ice to form and stick around on land than it is for them to form on the open ocean, which acts as a giant heat reservoir. Because the northern hemisphere has all this land, it provides the perfect foundation for glaciers to grow. When the climate starts to cool, snow that falls on North America and Eurasia during the winter can survive through the summer. Year after year, more snow piles up, compressing the layers below into dense glacial ice. This process is much less effective in the southern hemisphere, where most of the area at the right latitudes is ocean. While Antarctica is a massive ice-covered continent, it's surrounded by water, which limits the ice's ability to expand much further. This is why Milankovitch's theory zeroes in on the amount of summer sunlight reaching the northern latitudes. The fate of the world's ice isn't decided by how cold the winters get or how much snow falls. It's all decided by the summer. If the northern summers are cool, the winter snow and ice don't melt away. The ice sheets survive, and they can even grow. If the northern summers are warm, the ice sheets melt back, exposing the darker land and ocean beneath. The northern hemisphere is the critical tipping point for Earth's climate system. Let's dive into the first of Earth's big climate-changing dance moves, its axial tilt, which scientists call obliquity. You probably know that Earth is tilted on its axis. It's not sitting perfectly upright as it spins. This tilt is the reason we have seasons. When the northern hemisphere is tilted toward the sun, it's our summer. When it's tilted away, it's our winter. Right now, our planet is tilted at about 23.5 degrees. But here's the amazing part. That tilt isn't fixed. It actually rocks back and forth very, very slowly over time. This rocking motion is caused by the gravitational tugs of other planets in our solar system, especially the giant Jupiter. These gentle nudges cause Earth's tilt to vary between about 22.1 degrees and 24.5 degrees. It takes about 41,000 years to complete one full cycle from one extreme to the other and back again. That might seem like a tiny change, just a couple of degrees, but for the planet's climate, it's a huge deal. This change in tilt directly affects the intensity of the seasons. A greater tilt means more extreme seasons, while a smaller tilt means milder ones. When the tilt is at its maximum around 24.5 degrees, the poles receive more direct sunlight in the summer. This leads to much warmer summers in the Arctic and Antarctic regions. For the northern hemisphere, the towers, these in on the Scalver, these extra warm summers are very effective at melting away the ice and snow that accumulated during the winter. With less ice cover, the planet absorbs more sunlight and warms up, making it very difficult for an ice age to start or continue. A high tilt is like turning up the summer heat in the north, promoting a warmer, interglacial period. On the other hand, when the tilt is at its minimum, around 22.1 degrees, the seasons become much milder. The summers in the polar regions aren't as warm because the sun's rays arrive at a less direct angle. These cooler summers are less effective at melting the previous winter's snow. If snow and ice can survive the summer, they start to build up, reflecting more sunlight back into space and cooling the region further. A low tilt, therefore, creates the perfect conditions for ice sheets to grow, helping to push the planet toward an ice age. This 41,000-year rocking motion is a fundamental beat in Earth's climate rhythm. Our planet's next big move in this cosmic dance is a change in the shape of its orbit around the sun. We often draw Earth's orbit as a perfect circle, but that's not quite right. Earth's path is actually a slightly stretched out circle, or an ellipse. Scientists call this deviation from a perfect circle eccentricity. Just like the planet's tilt, the shape of this orbital path changes over time. It cycles from being nearly circular to being more elliptical and back again. This cycle is a long one, taking about 100,000 years to complete. What causes this change? Once again, we can thank our giant planetary neighbors, Jupiter and Saturn. Their immense gravity pulls on Earth, subtly stretching and squeezing our orbit over vast stretches of time. When the orbit is nearly circular, the distance between Earth and the Sun stays relatively constant throughout the year. This means the amount of solar energy Earth receives is pretty stable from month to month. But when the orbit becomes more elliptical or eccentric, the distance between Earth and the Sun varies much more significantly over the course of a year. When the orbit is stretched out, there's a point where Earth is closest to the Sun, called perihelion, and a point where it's farthest away, called aphelion. This difference in distance can change the amount of solar energy we receive by more than 20% between these 2 points. That's a significant variation. A more eccentric orbit essentially exaggerates the effects of being closer or farther from the Sun. It can make seasons more extreme or more mild, depending on where Earth is in its orbit during different seasons. This 100,000-year cycle is currently the dominant beat in the Ice Age rhythm. Right now, Earth's orbit is not very eccentric. It's quite close to being a circle. We are slightly closer to the Sun in January and farther away in July. This actually makes northern hemisphere seasons a bit milder. Our winters are a little warmer and our summers a little cooler than they would be otherwise. But as the eccentricity cycle continues, this will change. The shape of our path is a slow, powerful driver of climate, working in concert with the other cycles to determine when our planet has enough of a solar energy shift to trigger an ice age. The final move in Earth's climate dance is a wobble. Yes, our planet wobbles like a spinning top. If you've ever spun a top, you've seen how its axis slowly traces a circle as it spins. Earth does the exact same thing, just on a planetary scale and over a much longer period. This slow wobble of Earth's rotational axis is called axial precession. It's primarily caused by the gravitational forces of the Sun and the Moon, pulling on Earth's equatorial bulge. This wobble means that the North Star, our axis, points to changes over time. Today it's Polaris, but in about 13,000 years, it will be a different star, Vega. This wobble takes about 26,000 years to complete one full circle. Now why does this matter for climate? Because precession changes the timing of the seasons relative to Earth's position in its orbit. It determines which season, summer or winter, occurs when Earth is closest to the Sun, that's perihelion, or farthest away, that's aphelion. This is a critical piece of the puzzle, as it can either amplify or dampen the seasons, especially when the orbit is more elliptical. It's kind of like changing the timing of a drum beat in a song. It can completely alter the rhythm. Let's look at an example. Today, the northern hemisphere's summer happens when Earth is farthest from the Sun. This makes our northern summers a bit cooler and milder than they would be otherwise. But about 13,000 years ago, halfway through the precession cycle, the situation was reversed. The northern hemisphere was tilted toward the Sun when Earth was closest to it. This resulted in much hotter northern summers and colder winters. Those hotter summers would have been very good at melting ice sheets, helping to end the last ice age. So, precession acts like a toggle switch for seasonal intensity. When northern summer aligns with the closest point to the Sun, you get super hot summers that can melt glaciers. When northern summer aligns with the farthest point from the Sun, you get milder summers that allow ice to persist and grow. This 26,000-year wobble works hand in hand with the 100,000-year eccentricity cycle. When the orbit is very circular, precession doesn't matter much. But when the orbit is highly elliptical, the wobble's effect on seasonal sunlight becomes extremely powerful, making it a key player in the Ice Age story. Now that we know the three individual dance moves, the 41,000-year tilt, the 100,000-year orbital shape, and the 26,000-year wobble, we can see how they combine to create Earth's climate symphony. These cycles don't operate in isolation. They overlap, interfere, and reinforce each other in complex ways. It's the combination of all three that determines the precise amount of summer sunlight reaching the crucial northern latitudes. Sometimes the cycles work together to push the climate in one direction, and other times they can cancel each other out, leading to more stable periods. Imagine you have three different spinning dials, each turning at a different speed. The first dial controls the intensity of the seasons, which is the tilt. The second dial controls the overall variation in distance from the Sun, or eccentricity. The third dial controls when the seasons happen during that orbit, which is precession. An ice age is most likely to begin when all three dials line up to create the coldest possible summers in the northern hemisphere. This perfect storm for an ice age would be a combination of low tilt, high eccentricity, and a wobble that places northern summer at the farthest point from the Sun. This combination minimizes the amount of solar energy available to melt ice in the north. The low tilt means milder seasons overall, so summers aren't very hot. The high eccentricity means Earth is very far from the Sun during one part of its orbit, and the wobble ensures that this faraway point is happening during the northern summer. The result is a series of very cool summers, where winter snow doesn't melt, snow piles up, compacts into ice, and the great glaciers begin their slow advance across the continents. This is how a long, cold ice age can be triggered. Conversely, the end of an ice age is triggered when the cycles align in the opposite way. A period of high tilt, high eccentricity, and a wobble that places northern summer at the closest point to the Sun creates incredibly hot northern summers. This intense summer sunlight acts like a giant blowtorch on the ice sheets. Melting accelerates dramatically, glaciers retreat, and the planet warms up, entering a warmer interglacial period, like the one we are in now. Scientists can see this pattern recorded in ice cores and deep-sea sediments, which show Earth's climate swinging back and forth in perfect time with the Milankovitch cycles. We've mentioned it a few times, but let's really focus on why summer sunlight is the most important factor in this whole Ice Age story. It might seem counterintuitive. You might think that what really matters for making an ice age is having brutally cold winters with lots of snow. And while cold winters are certainly part of the equation, they aren't the deciding factor. No matter how cold a winter gets, it can always get cold enough to snow in the high northern latitudes. The real question is not how much snow falls in the winter, but how much of that snow survives the summer. Think of building an ice sheet like building a savings account. The winter snowfall is your income, the money you deposit. The summer melt is your expenses, the money you withdraw. To grow your savings, you don't necessarily need a huge income, you just need your income to be greater than your expenses. In the same way, to grow an ice sheet, you don't need record-breaking snowfall. You just need the summer melt to be less than the winter snowfall. Cool summers are the key to reducing your expenses and letting your ice savings grow year after year. This is why Milankovitch focused his calculations on insolation, the amount of solar radiation, during the northern hemisphere summer. When the Milankovitch cycles align to deliver less sunlight to the north in summer, the snow from the previous winter doesn't all melt away. A patch of old snow remains. The next winter, more snow falls on top of it. The next summer, which is also cool, a little more of that snow survives. Over centuries and millennia, this accumulating snow compresses under its own weight, transforming into dense, solid glacial ice. This is how a small change in summer energy can lead to a colossal ice sheet. Once an ice sheet starts to grow, it begins to help itself. Ice is bright white and highly reflective. While dark ocean water or forests absorb a lot of the sun's energy and heat up, a white sheet of ice reflects that energy right back into space. This creates a cooling effect, which makes the summers even colder, which allows even more ice to survive, which reflects even more sunlight. This process, known as a positive feedback loop, is a powerful amplifier. A small initial cooling from the Milankovitch cycles can be magnified by the growing ice itself, pushing the climate system over a tipping point and into a full-blown ice age. Let's talk more about that amazing feedback loop. The scientific term for how much sunlight a surface reflects is albedo. Something with a high albedo, like fresh snow or ice, is very reflective and stays cool. Something with a low albedo, like dark soil, asphalt, or open ocean, absorbs a lot of sunlight and heats up. You've experienced this yourself. Walking barefoot on a white sidewalk is much more comfortable on a sunny day than walking on a black asphalt road. The ice albedo feedback is one of the most powerful amplifiers in Earth's climate system. Here's how it works to start an ice age. The Milankovitch cycles cause a slight cooling in the northern summers. Because it's a bit cooler, not all the winter snow melts. This leftover snow increases the albedo of the land. Instead of dark ground absorbing sunlight, you now have a bright white patch reflecting it. This reflection means less heat is absorbed, which makes the local area even cooler. This, in turn, allows even more snow to survive the next summer, which makes the reflective patch bigger, which cools the area further. The cycle feeds on itself. This feedback loop is how a small, gradual change in solar energy from the Milankovitch cycles can be magnified into a massive, planet-altering event. The initial push is small, but the ice albedo feedback takes over and does the heavy lifting, driving the planet's temperature down significantly. It's a classic tipping point scenario. Once enough ice has formed to substantially change the planet's overall albedo, the climate system is locked into a cooling trend that is hard to reverse. The ice's icy grip takes hold, and the glaciers advance. The same feedback loop works in reverse to end an ice age. When the Milankovitch cycles shift to create warmer northern summers, the melting begins. As the giant ice sheets start to shrink, they expose the darker land and ocean beneath them. This darker surface has a lower albedo, so it absorbs more sunlight instead of reflecting it. This absorption of energy warms the planet, which causes more ice to melt, which exposes more dark surfaces, which absorb more heat, and so on. This warming feedback loop accelerates the collapse of the ice sheets and pulls Earth out of an ice age and into a warm interglacial period. It is absolutely crucial to understand the timescale of these natural climate rhythms. The Milankovitch cycles operate on vast timelines, 26,000 years, 41,000 years, and 100,000 years. The climate changes they cause are incredibly slow and gradual, unfolding over thousands of generations. They are the deep, slow drumbeat of our planet's history. These cycles have dictated the ebb and flow of ice for millions of years, and they continue to operate in the background today. According to these cycles, Earth should be in a very slow, long-term cooling trend that would eventually lead to another ice age tens of thousands of years from now. However, the climate change we are experiencing today is happening at a completely different tempo. What we have observed over the last century is not a slow, gradual shift. It is a rapid, steep warming that is happening on a timescale of decades, not millennia. The speed of this change is what makes it so different and so concerning. While the Milankovitch cycles might change global temperatures by a few degrees over 10,000 years, we are seeing comparable changes happen 100 times faster. This is not the natural rhythm of the planet. This is a sharp, sudden fever. The cause of this rapid warming is also different. The driver of the Milankovitch cycles is the predictable, clockwork-like variation in Earth's orbit and rotation, which changes the distribution of solar energy. The driver of modern climate change is the rapid increase in greenhouse gases, like carbon dioxide, in our atmosphere. These gases, released from burning fossil fuels, trap heat that would otherwise escape into space, warming the entire planet. This is a completely different physical mechanism from the one Milankovitch described. It's an additional warming force laid on top of the natural cycles. Understanding the Milankovitch cycles is essential for climate science. It proves that our climate is sensitive to changes in its energy balance, and it provides a baseline against which we can measure the changes happening today. The science is clear. The slow, majestic dance of the planets cannot explain the frantic, high-speed warming we are now witnessing. The current warming trend is due to human activities. By understanding both the natural rhythms of the past and the new, rapid beat of the present, we can better appreciate the profound impact we are having on our home planet.